Hi, I'm Tianwei Xiong, and I'm glad to introduce EVATok, Adaptive Length Video Tokenization for Efficient Visual Autoregressive Generation. The motivation of adaptive length video tokenization can be revealed in the examples here. So we have three AI-generated videos. Up left is very dynamic, the complex layout. And up right, complex layout but relatively static. And bottom, it is simple and static. And we can intuitively feel that they don't worth the same computation to generate. And if we look at their file sizes after MP4 compression, it's more clear. They don't worth the same computation. But for traditional video tokenizers, different videos are basically using the same computation. Whether they are using VIT-based architecture or CM-based architecture, they just encode videos into temporally uniformly distributed causal token sequences, and all samples are given the same token budgets. So this uniform computation allocation is intuitively not reasonable. Computation is over-allocated to easy parts while underserved to complex parts. So EVATok targets to adaptively assign more tokens to complex or dynamic samples or parts, and less tokens to simple or repetitive parts. That makes efficient adaptive video tokenizer, EVATok in short. Here's one example. So this is a 16-frame video. We split it into 4 blocks, so 4 frames per block, and its content is simple and repetitive. And traditional methods would assign the same number of tokens to all blocks, as illustrated by these little rectangles with different colors. But for EVATok, only the first block is assigned 256 tokens, and for the rest, as few as possible. And finally, in a fair comparison setting, this assignment keeps the same LPF score with only 1/3 the cost. And for more examples, in example B, when the layout becomes very complex, but the content is still static, EVATok automatically assigns more tokens only to the first block. Compared to traditional methods, tokens are less, and the LPFS is even better. In example C, when there are changes in the content, more tokens are assigned to the corresponding parts, and in example D, more tokens will be assigned to all parts for very dynamic and challenging content. And if we look at the overall quantitative performances, EVATok achieves superior reconstruction, downstream generation, and token cost trade-off. So how do we design EVATok to achieve this performance? The core problem we need to solve is how can the algorithm know what is the optimal token assignment for different parts. So we don't have any data specifying how to optimally assign tokens to different video parts according to the content, and the human label is almost impossible to obtain. But we can limit the range of possible choices through quantization and try every possible assignment to find the best one, and that is basically the idea of EVATok. But how can we define best assignment? Assignment is how many tokens are assigned to each causal temporal token block, and we want the token sequence to be short, but we also want the reconstruction quality to be good. So we define a reward to measure how good an assignment is. So it contains 2 parts. One part is the reconstruction quality of this video given the assignment A. This is the outcome, the return. So it's the more the better. Another part is the total token count. Is the cost, so the fewer the better. And the best assignment is the assignment A that delivers the highest reward. Now we have a definition of the best assignment. So ideally we can traverse all possible assignments to find the best assignment. This can give us a dataset including videos and their best assignments, on which we can train a lightweight router for optimal assignment prediction, and with this router we can train adaptive length video tokenizers. So when compressing a video, a router first predicts the optimal assignment according to the content of the video, and the tokenizer takes the assignment and the video to encode it into a sequence accordingly. As for how to curate this router training dataset, we have 2 stages for it. In the first stage, we train a proxy tokenizer. A proxy tokenizer is a tokenizer that can compress any video according to any given assignment from a candidate assignment set. So there are input videos, and we randomly choose an assignment from the candidate set and reconstruct the video according to the random assignment. And that's its training process. This proxy tokenizer will be used for the reward calculation in stage 2. And stage 2, the router training data curation, is to build a dataset of videos and their optimal assignments for training routers. We traverse a video dataset and record the video assignment reward triplets for all possible assignments, and further for each video through selecting the highest reward assignment. We can build a dataset of videos and their optimal assignments for compression. And together, we have a 4-stage framework of EVATok, and the outcome of this framework is the combination of a router and a final tokenizer. As for the architecture of our adaptive length tokenizer, it is a Q-former-based tokenizer given a specific token assignment. The 1D causal query will be initialized accordingly, and all the attention masks are temporally causal, therefore it can handle variable length assignments. In our validation experiments, using EVATok design with a router on UCF 101 benchmark, the video reconstruction and generation is improved while the total token length achieves at least 24.4% saving compared to the traditional uniform token assignment setting. And when comparing with other methods, EVATok achieves at least 24.4% cut in token length, meanwhile it achieves comparable or better performances in video reconstruction and downstream video generation. EVATok has changed many traditional settings, and that of course brings questions and concerns. So first, EVATok is a 1D tokenizer. So removing special prior in token sequences means some useful techniques for video generative models cannot be easily used, like rope 3D and block sparse attention. And when curating dataset, EVATok tries every possible solution to find the optimal assignment. But for longer videos, the possible assignment would increase exponentially. And that's also a problem. But as for the exponential explosion problem, it can be solvable. Just need to search autoregressively to truncate the searching space. So in conclusion, EVATok reveals that adaptive length video tokenization can save budgets and improve performances in reconstruction and generation. An adaptive assignment can be given by a lightweight trainable router, and the training data for it can be collected through exhaustive searching and traversing. And that's the presentation. Thank you for listening.